different works. One is 3 years old, and the other one is Work to Appear. So it's kind of a combination of both of them. The main emphasis is going to be on the more recent work, which is going to be, which is not out yet. So 5-dimensional black holes were studied in the mid-90s, and they were among the first black holes studied in the post-duality era in string theory. And these black holes, the black holes that were constructed, they were in various ways. For concreteness, let me focus on two specific ones. In the type 2b description, one took the geometry to be 4 torus times a circle, or K3 times a circle. And in the M-theory dual description, you could, the first one is equivalent to T6, and the second one gets related to K3 cross T2. So those were the two specific geometries one studied. And also one considered specific objects in this category. In the context of type 2b, when we talked about K3 or T4, this is the so-called D1, D5 brane construction, but it's easier to think in this context by duality as D3 brane, where you take the D3 brane wrapped around the Riemann surface inside K3 or T4 times a circle. So you take a D3 brane in K3 times S1 or T4 times S1 as being part of a Riemann surface inside K3 or T4 times a circle. So it's a 3 brane wrapped around this 3-dimensional geometry. So it will correspond to particles in 5 dimensions. And the M-theory description from 11 to 5 is on T6 cross K, or K3 cross T2. In that context, it corresponds to M2 branes wrapped around 2 cycles in this geometry. And they are dual to one another. That's a well-known fact. And so let me just, for simplicity again, restrict to K3. And if we focus on K3, and if you take a genus G curve inside K3, you get the moduli space of D3 branes that wrap around the genus G curve corresponds to a sig model. So in other words, you go D3 brane on a Riemann surface, you get a 1+1 dimensional theory left over on D3 brane. So it's a sig model whose target space is the symmetric product of K3 to the power of G, where G is the genus of the curve, times an extra R4, which is the transverse direct dimensions to the string. This is the moduli space. In the case of there are different description. When you want to talk about the black hole, you take that string and you talk about a momentum around the circle for that string. And in the context of that string, it corresponds to the elliptic genus because you're taking a momentum around the circle. So you compute the elliptic genus of this sig model. On the other side, on the M-theory side, this n, which is the momentum here, gets related to the number of elliptic fibers of M2 branes wrapping the T2 of the elliptic fiber. So it's an extra T2, which is invisible in this side, and that's the usual duality. So you talk about a Riemann surface in here, which is glued to n copies of T2. So in the right-hand side, it's purely geometric. In the left-hand side, it is the elliptic genus of a sig model. So this maps the elliptic genus of the resulting 1+1 dimensional theory with momentum n to computations of M2 branes in this geometry. So on the right is purely geometric. And there's a holographic statement of this, which is if you take ADS3 times S3 times K3, in other words, if you look at that string without talking about the elliptic genus as a string itself, it's holographically dual to symmetric product of K3 G copies. And this is a well-studied holographic duality. So the theory in 2 dimensions will have a 4,4 supersymmetry. The transverse to the string is transverse R4. The string has an SO4 action. On it, the Lorentz group is SU2 left and SU2 right, which gets related to the SU2 left and SU2 right of the corresponding 4,4 algebra, the little n equals to 4. And you can compute the central charge. In particular, the left-moving central charge is 6g plus 6. And as I just said, the momentum of the strings with momentum n gives you a particular 5D string that people study. And the entropy of the strings goes like 2 pi in the leading order for large n, will go like this kind of formula, this Cardi-like formula with the central charge given by this. And this is agrees with the old results of Wittgenstein and Hawking in this limit. So, and the 5D BPS black holes can be extended to the spinning ones if you take into account the further SU2 left. In other words, in addition to the momentum, if you take into account the spinning on the SU2 left, the left side, this spin gets related to the SU2 left supersymmetric spinning 5D black hole, and you can actually enumerate not just the charged black hole, but also spinning and charged black hole. Okay, now I want to, so this is kind of a review of old stuff, basically to put it in the context of new stuff, newer stuff. So in the context of M theory, we can reduce the amount of supersymmetry in the box. So we said that in the M theory context, the geometry that I was just talking about reduces to K3 cross T2 from 11 down to 5, but it's natural to generalize that to Calabi threefold. So if you take Calabi threefold and you can talk about M2 brane wrapped around this geometry, you can do the same kind of game. For example, if this is conifold, if this is quintic, for example, in the context of quintic, you can talk about M2 branes wrapped around 2 cycles of quintic and talk about the 5D black holes. Nobody has studied that, surprisingly enough, after all these years. We don't have an answer to counting let's say, the black hole states of the quintic in 5 dimensions and checking it that it agrees with Wittgenstein and Hawking. It's a good thing to do, but we haven't done it. So for general Calabi, we do not know how to compute these. And in fact, the reason is that the nice thing about this picture was that there was a type 2b side on the other one where we had a string, and the elliptic genus of that string gives us the black hole formula. So the question is, what can you do for the Calabi threefold, which gives you a string, so you can do the same game? But before I do that, the computation of the partition function of M2 branes on Calabi threefold is related to counting of the topological string partition function. So if we knew the topological string partition function, it is equivalent to knowing the black hole entropy or black hole degeneracies for spinning black holes related to the Calabi. But we don't know the full topological string amplitudes for the Calabi threefold, so we do not know how to compute it. So we do not know all genus topological string amplitudes, so therefore this cannot be done. And we need to still look for a string, so what do we do? So to get a string, we can if the Calabi is elliptic. So if the Calabi threefold is elliptic, so basically as in the type of threefolds that we are used to in the context of F theory, we take a 4-manifold with an elliptic fibration to make a threefold. And then we have the usual description that if you take the F theory and then go down one more circle, then you get M theory on X. So in other words, if you go down in F theory from 12 to 6 dimension on this geometry, and if you go further one more dimension down to 5 dimensions, that's equivalent to M theory on that Calabi threefold, and therefore we can try to talk about this particular geometry. Moreover, D3 branes wrapped on B4 times S1, D3 branes wrapped around this get again related to the M2 branes wrapped around N times T2 with this Riemann surface on B4, exactly like in the K3 case. So in other words, restricting to K3 or T4 does not give us much advantage really in terms of a string. We can do this much more generally than had been done in the context of K3 or T4. And in fact, not only could have been done, it has been done long ago again. So this relation with the F theory and trying to use the string in the context of F theory to do this was already studied a long time ago. And it gives you can study the corresponding string, in this case, a string that you get as 0,4 supersymmetry. And you can compute the central charge. It depends on the genus of the curve and also the first Chern class of the bundle times the class of the curve that you're wrapping, some left and right central charges that you can compute. So this gives you a way to compute the elliptic genus, and you can get some descriptions out of it. And you can actually push this to lead to a holographic statement in the context of F theory, as was done in this paper and some more recent work. I believe there was a talk on Monday here about this by Laurie. Is that correct? So there was a related discussion here about holographic duals that this string will give you. Namely, you take D3 brane wrapped around a Riemann surface, and if you look at the corresponding string, now there's a more general holographic statement, which is AD as 3 times the base of this elliptic threefold, being dual to a CFT with 0, 4 supersymmetry. So instead of 4, 4 that we had for K3, it becomes 0, 4. And the elliptic genus of this conformal theory would be the topological string partition function of X will be the partition function of the black hole, spinning black hole. So these statements have different interpretations and meanings, but they're all connected by chains of dualities between them. These are, you could say, conjectures, yes, but more or less conjectures which are already follow from other dualities. So if one believes the other dualities, you have no choice, in other words. So yes, you could call them conjectures, but not new conjectures. It's like 20, 30 years of conjecture, 20-some years conjecture. Now, the only emphasis is the fact that we take this seriously as an object, which we studied already in 2015, and it was studied also more recently. And this object by itself has not been studied as much holographically, except for some general facts about them. So people do not know as much about this class as, let's say, for when B was K3. But the question is, how do we actually describe these 0, 4 to these CFTs? So in the other cases, we had the sigma model and symmetric price of K3. That was nice and looked simple. Of course, it's deceptively simple because sigma model on K3 is not necessarily trivial. And then you take symmetric products of it on top of it, so it's not that trivial. Computation of the elliptic genus of it was easy. That's been done in closed form. So that's at least the good part of it, but explicit description of the sigma model is not necessarily trivial. And especially, the interesting point turns out to be when you take symmetric products, you have singularities that you have to resolve when K3s come together, when you mod up by permutation of the K3s. And to get a good gravity dual, you really need to blow up. And then those correspond to the regime of a sigma model where we do not have any closed form, including no techniques we know in orbifolds or whatnot, because we have to blow up. So, okay, so then the idea here is, what can we do? So here, we would like to come up with some kind of a picture about what the 0, 4 2D CFT looks like. And that's basically the aim of the rest of the talk, is to come up with some descriptions for this, for the CFT, 2D CFT. So, and the hint is this. There's 1, 60 superconformal theories. If you study them, they are known, of course, to give 0, 4 quivers for some cases, and we know they're quivers. They will give you 0, 4 strings. So these are 60 1, 0 theories, as we know, have strings in them, and the strings have 0, 4 supersymmetry. In a number of cases, people have studied what kind of quiver gauge theory you get on the word line of these word sheets of these strings, and therefore studying them might be a hint about what is the strings living, what do these things look like. That's the basic aim. So the idea is to use these as local ingredient and stitch them together to get the CFT for the global model. That's basically the hope or the idea. So let me talk about the specific classes that I want to focus on. So you take the elliptic threefold to be in the non-compact version first. Take it to be T2 times C, where the T2 is the elliptic fiber, as in the usual case, and I take the base to be non-compact. Mod that by Zn times Zm, where Zn is some generated by some nth root of unity alpha and mth root of unity beta. Of course, alpha and beta should be such that they fit into the symmetries of T2, so they cannot be arbitrary integers. And so this gives you a singular geometry when you're at the origin of C, the Z1 and Z2 equals 0, you get a singularity, and people have studied the kind of 60 superconformal theories you get at the origin. So you get 61, 0 superconformal theories, and these are list of some of these cases that we will be interested in. For example, if you take Z2 times Z2, you get SO8, you get this superconformal theory corresponds to the E string with the global symmetry which corresponds to the Z1 equal to 0 line or Z2 equal to 0 line, where these are the complex lines where they meet at the point where the singularity is. So, so these corresponds to SO8 global symmetries, gauge symmetries on the 8-dimensional sense, which corresponds to, so from the F theory viewpoint, they're on the 7 brane, which corresponds to global symmetries from the viewpoint of the 6T theory. So you have SO8 on one side and SO8 on the other side, and the point they meet corresponds to this E string. Here, you mean? So if you take, let's just do the simple case first. So take a Z2 here, -1, -1, 1. In that context, you will get, forget about this other one, you get at Z1 equal to 0, you get an SO8 gauge symmetry. This is just a singularity of the elliptic vibration. In this case, you can actually do even perturbative, a la Sen description, and you get the usual SO8 of orientifold and all that. So that's a simple example. But you can do it more generally and you get all these pictures I'm saying here. So you get SO8 on one, SO8 on the other, or depending on which ones you do, you get different kinds of gauge groups living on Z1 is 0 or Z2 equals 0. These are 7 branes. You can think about these as 7 branes intersecting and giving you a singularity. You can blow up the singularity. You get different lists of the conformal theories that you get in 6D. So you get the usual E's and all that, and also depending on whether they are, how the Z2 and Z3 act, you can get also the outer automorphism into the action and get some things like G2 and F4 and all that stuff. So you get some interesting lists here. So this is a non-compact, the case of a non-compact base in F theory. But now we are interested in replacing C times C with T2 times T2. So what are we going to do then? Well, the local part of the story is the same. Namely, you can just look at every singularity and see what happens. So that part, we can just view it. We get a local picture. And somehow we need to connect these points together in some way. So let's do a simple case. This is T6 modded by Z2 times Z2. So these are the two Z2 directions, T2 directions, which used to be C and C before, complex plane. And before the Z2 times Z2 had only one fixed point at the origin, joint fixed points. But now, each one will have 4 fixed points on each of the tori. So you have 4 times 4, 16 fixed points. So instead of having one E string theory, you have 16 of these E string theories, depending on which point on the fixed points of the tori you're at. And moreover, each one of them passes through by a 7 brane, which is an SO8 on one side, another 7 brane SO8 on the other side, the one horizontal and one vertical one, depending on whether you're wrapping around this T2 or the other T2. So, now previously this SO8 was just the global symmetry, but now you have a compact T2. So therefore it's gauged. And moreover, this T2 is already modded by Z2, so it's just a P1. But it's actually 4 points that are blown up on it. So basically, this geometry of this particular line is O minus 4 over P1. So the geometry of this guy is like another P1 with an O minus 4 on it. And so this SO8 itself is part of the T2, which is now part of an SO8. So in other words, what's happening is that every one of these lines is stitching together 4 of these ones. Each one of them has an SO8, and you're gauging the global symmetry of these 4 O minus 1 theories by the corresponding SO8 with an O minus 4 over P1 geometry. In other words, that SO8, let's say it's one of them corresponds to O minus 4 over P1 geometry, which is gauging the common SO8 of those 4 O minus 1 of those E strings. And the same with the other 4 and the other 4 and the other 4. And some of them are vertical and some of them are horizontal. In other words, as you remember, we had vertical direction and the horizontal directions. So the geometry of the full geometry of the gauged quiver looks like these local geometries of these O minus 1 curves with the 4s which are gauging them and connected in this particular way. Now you can check that the gravitational anomaly cancels. This is not this part is the fact that this Lincoln diagram is related to affine. It is related to the little string version of the same theory. If you adjust on T2 times C. Well, I will show you some other ones. So the anomalies cancel, and also you can check that the mixed gravitational gauge anomalies also cancel. And you can also show that the lattice of these cycles, this lattice of the cycles, has some null directions, and if you mod it by that, you get a self-dual lattice, as it should be. Integral self-dual lattice, as you need for a gravitational theory. So everything looks good as far as consistency for gravity. So this looks like potentially a complete model of the non-gravitational sector of this theory. It includes gravity because it includes gravitational statement in the sense that it cancels anomaly, which does include the gravitino multiplet and all that. So gravity is part of the story, but I'm just describing the non-gravitational sector of that theory. Yes. We didn't have 16 SOAs. We had only 8. We had 4 vertical and 4 horizontal. And there are 16 O-1 E-string theories. So there are 16 intersection points. But there are only 8 SO8s. Okay. Let me just give you a few more examples. You can do this, for example, for T6 modded by Z times Z3. The story is similar. For each one of them, you get O-3 here. Well, each one of these points corresponds to a 1, 3, 1 with an SU2 gauge theory on that 3. And then you have over here, you get an O-6 theory instead of the O-4 that we had. You have an E6 global symmetry, which now gets gauged because it wraps over a compact 2. So you have the same. So the same picture now is just to give you a description. Again, you can check the anomalies cancel in a non-trivial way. And also you can check the lattice is self-dual and so forth as expected. You can do more examples. Let me not bother by saying it. Anyhow, you can see, you can get an interesting combination of the gauge and so on. Depending on which one is going where, you get E8 one side, F4 the other side, etc. Depending on which lines, you might have more interesting geometry than the one I told you. But so you can get an interesting system of gauged objects. And each one of them you can check works in terms of anomaly cancellations and all that. So it looks like this at least has all the right features to be the complete non-gravitational sector of the theory. In fact, for the Z2 times Z2 model, we have a concrete covert description of the strings. Namely, from the previous works on the local covert theories that you get for the O-1 theories, you can actually write down the theory that you get on the corresponding string on the 1 plus 1 dimensional strings for the 0, 4. And you get a collection of these strings with certain ranks involving SO and SP, OK and SPN gauge theories on these strings. So you get a collection of OK and SPN. So these ones corresponding to the string wrapping numbers gives you the rank, relates to the K, in other words. And the string wrapping number for this cycle corresponds to this N. So you can write the corresponding covert theory for these guys. So we would get a holographic statement if you just take this 0, 4 strings viewed as a covert theory that you would ascribe to ADS3 times S3 times, in this case, T4 modded by Z2 times Z2, which is what the case of the Z2 times Z2 I told you about, with this corresponding cover. Some particular combination of O's and SP's, which looks concrete enough. So how do we know this is correct? Well, we don't know. So how can we check some aspects of it at least? Well, we can compute the anomalies, and in fact, we expect the C left and C right, the anomalies on the corresponding 0, 4 theory. We can use the two things. We know from geometry what it should be. From the geometry, we know what we expect the left and right central charges to be. But we can actually now use the quiver itself to compute it. So using the quiver itself, we can compute the C left and C right, and we get what we expected based on the anomalies that we expected. And in particular, if you compute the elliptic genus using these formulas for the corresponding quiver gauge theory, you will get that the prediction will be that the elliptic genus of this quiver will give you the topological string on T6 divided by Z2 times Z2, which is the partition function of the black hole. And there are these concrete formulas one can write down, because since these are quiver, you can actually explicitly write the elliptic genus. Well, there are some complicated integrals you need to do, so even though this looks in some sense closed form, it's not trivial to do these integrals necessarily, but at least there's a closed form for it. Yes, so the only non-trivial test we have done, which I just already mentioned, is that the C left and C right agrees with the black hole count. So the quiver knows about black hole. So in other words, if you compute the elliptic genus of this guy, the leading growth is the same as Beckett-Stein-Hawking. It doesn't prove it's the correct formula either. In fact, I have to say one fact which shows that there's some aspect of it which needs to be completed. So let me explain this a bit more clearly. This T4 has complex structures. The complex structure of the T2s, which for the quiver that we wrote down doesn't show up. So it cannot be the complete story in the sense that I'm not giving you the parameter which deforms the complex structure. So we expect that only at the very specific complex structure this could be the quiver at best. And the natural expectation is that you take this T4 and you take a degenerate complex structure. In that case, the theory becomes just this quiver. That's, I think, what the more natural guess is, because it's very unlikely that just a pure quiver theory arises in a compact model. So the more natural explanation would be that you take the complex structure and degenerate it, and then in that limit, this may be exact quiver theory that you get, but computation of to the extent that the topological string may or may not depend on complex structure, this will give you the same answer. But that remains to be checked. So now, emboldened by this, we can go on to do the same thing for 5D. So if this is correct, and again I said there's a big if there, then you will be getting a topological string partition function for compact Calabi-Yau for the elliptic threefolds, and we can get ambitious and say, well, what about non-elliptic? Can we say anything about them? Well, the basic idea we used in the case of the 6D was the super-conformal theories that we had in the picture, and we stitched them together to get this non-gravitational sector of this F-theory geometry. So we could try to do the same thing for Calabi-Yau threefolds. For example, for quintic, or mirror quintic in particular. And in fact, if you take the quintic threefold and mod that by Z5 cubed, this is also known as the mirror quintic, we do get 5D super-conformal field theories that people have studied at various singularities. Indeed, for every triple of points being 0, we get a geometry which is what's called the T5 conformal theory in 5D, where the geometry is C3 divided by Z5 times Z5s. So this is a well-known singularity, which is the 5D version of these Gayotto theories that people have studied already in 5D. So these, for every triple of them, so there are going to be 10 of these guys, 5 choose 3. So there are 10 super-conformal theories in 5D. Now, for every pair of them, there will be an A4 singularity. That means there's a curve in the M-theory geometry, which will have an A4 singularity, therefore an SU5 gauge symmetry on it. So what happens is that the basic story is this. Let's say take one of these singularities. So you get a conformal theory, which in the language of toric geometry looks like this, or in the web diagram language it looks like this web. There are 5 external lines in the web language which corresponds to SU5 global symmetries for the conformal theory. But now those SU5 global symmetries are compact on a P1 curve, so they get gauged. Very much like those SOAs I had before in the context of the Calabi-Yau in the elliptic threefold case. So they have to be gauged. So you basically get a collection of, so each triangle here corresponds to one of these conformal theories of T5. And each one of these circles corresponds to gauging some common SU5s of triples of these T5s. So this geometry here encodes the geometry of conformal theories and gauged in this particular way. No, this is gauged, all of them gauged. Yes. So you can count the number of moduli. You can count that the number of the dimension of the Calabi-Yau moduli comes at there are six moduli coming from these 6 holes here. So there's 1, 2, 3, 4, 5, 6. There are 6 of them. And then there are 10 choices of these things, given 10 triangles. So there are 6 times 10 moduli coming from those singularities. And then there are SU5, and there are 10 of these circles. So there are 10 of those. Each one of them has 4 cartans, so that's the 4 of the SU5. And then there's one overall size of the quintic, which controls the coupling constant of SU5. And this gives you the 101 moduli of the mirrored quintic. So we can enumerate all the moduli of the mirrored quintic purely in terms of gauge theory data. So the 5D gauge theory data completely captures everything we want in terms of the geometry of the quintic, mirrored quintic. This is the geometry. You're just seeing this close. This is literally the picture of the mirrored quintic. So people have drawn beautiful pictures about how the Calabi looks. This is literally the interconnections of all these triangles and so forth. And basically, you can read it off from the geometry of the pentagon. Each one of, I mean, this is the geometry. So there's C3 mod Z2 times Z5 is the local singularity. There are 10 of them. And each one of these is a P1, which connects up this way. So, so how do you compute the topological string amplitude for these guys? Well, for these guys, we know how to do it using what's called the topological vertex. And for these other guys, we need to come up with a new way of doing it. For the topological vertex, we usually have this picture, 1 plus, what we call the 1 plus vertex. But there's a mirror geometry for that, which is basically dualized this to this picture, which is basically a pair of pants now. And this is, for the standard topological vertex, we have an amplitude known in terms of the Shor functions. And for the mirror one, it was already proposed a while back by mathematicians and physicists studied as well. And you get a formula which comes related to the amplitude for the 2D quantum Yang-Mills amplitude. So it's much simpler than the usual vertex. And this has been generalized for the SUN gauging using basically the idea of Nekrasov's partition functions at 5D by Hayashi and Omori. And so it gives a generalization of this, what I call the 1 minus vertex, to correspond to gauging SUN with the corresponding amplitude, which is similar to the U1 case generalized now. So from this data, you can actually, this is the partition function explicitly written down, which is given in terms of these Coulomb branch parameters and so forth. Anyhow, there's a relatively simple formula, and gives us the basic data for which we can compute the quintic. Again, the same issue that I mentioned for the case of the T6 remains here. Namely, the quintic has 1 complex moduli, which does not show up in our gauge theory description. So the gauge theory description is insensitive to the complex moduli of the underlying complex moduli of the mirrored quintic. So at best, this is in some limit, that answer. And it's natural to expect it's in the degenerate limit, like psi goes to infinity or something. So we have to take this picture with a grain of salt in the sense that this could be the description of the quintic, mirrored quintic, in some degenerate complex structure limit. That's, to me, a more natural conjecture one can make. It'd be interesting to see to what extent this captured the topological strings in that particular limit on the complex structure. Usually the amplitudes of topological string do not depend on complex structure. That's precisely the point of the topological string. However, in the infinite limit, it might, because it's non-compact, so the order of limits might be important, and these need to be studied, and we are currently studying those aspects. So let me conclude. So we have seen that the local description of conformal theories and 5D and 6D are quite powerful in giving a description for the non-gravitational sector of 5D and 6D theories, even in compact setup. We can get potentially concrete holographic dual descriptions for AD S3 times S3 times the base of F theory in terms of 0, 4 conformal theories. And we have checked some leading aspects of the growth of the black hole, which agrees with the black hole expectations. But of course, much more checks need to be done. Thank you.
More questions?
Hi, so you had this 60 quiver that you got from all these 141s that you stitched together in this nice way. So then I think the claim was that you can, using the quivers for the minimal models of these 60 SCFTs, that you could stitch those together and come up with a quiver for the 2D theory.
Yes.
Is that? I guess I don't see why that should. Is it obvious that you should be able to stitch these the quivers together for the 2D in the same way that you did for the 60?
Well, you would think that the physics is local for them, so in that sense, yes, but it's not. I wouldn't say it's a proof. So the evidence that the black hole entropy that you count, namely the C left and C right, based on that agrees with what you expect geometrically, is a non-trivial check. But I wouldn't say it had to work. If that wouldn't work, I would agree with you.
So in all the quivers that you have for non-compact Calabi-Yau's, you have an extra symmetry, which is an SU2 that corresponds to refinement of topological string.
Yes.
So
in this case, related. So it's a good question that's being asked. So there's an extra SU2 that we don't expect in compact ones. Yes.
So you lose it somehow when you gauge?
No, I think it's related. No, we don't lose it. And I think that's precisely the reason that I expect this to be true only in the given degenerate complex structure. So in degenerate complex structure, you can gain extra symmetries that you don't have in a compact case. So that's related to that mismatch.
I wonder that this BPA states from M2 brane can also be counted by this topological string theory, and this partition function over topological string.
Sorry, I can't hear you.
Okay, so I'm wondering that the BPA states from M2 brane or Calabi-Yau four manifold, four manifolds can be also counted by this topological.
Yes. You're asking that question?
Yeah.
M2 branes for Calabi-Yau fourfolds?
Yeah.
Is that what you're asking?
Yeah.
Some aspects of it have been studied. Morally, the answer is yes, but the detail, I think people are beginning to think about it. There have been some recent papers trying to interpret the counting of Calabi-Yau fourfolds in terms of the same countings we have for Calabi-Yau threefolds, but it's not developed as much.
Okay, so yes.
Just a basic question. I was puzzled when you said no one's looked at the quintic. Isn't the Malacina-Strominger-Witten paper doesn't do the quintic?
No, no. They're doing it 4D, you're thinking. I'm talking about 5D.
Oh, didn't they do the
no, they were talking about in the M5 branes wrapped around the 4
device.
cycles times S1. Mm-hmm. And they give a 4D black hole.
Okay. Fine.
Not 5D. So nobody, and this is a challenge to this community, nobody has managed to study M2 branes wrapped around the quintic to count it. In fact, there's a misnomer. I think there's this incorrect perception by some people that the only way you can get the black hole formula is Alacardi. Then you have to have a string. That's not true. Quintic has no elliptic thing in it. There's no string in sight for the quintic. But it has to work somehow. So the quintic in M theory on quintic giving you a 5D theory, there should be a description of how the M2 branes of that give you black holes, and the counting does not proceed via a string. Well, how does it proceed? I don't know. Nobody has managed to bring that out, and I don't think it has been people have even studied it seriously enough.
Yeah, I was just wondering, can you try something similar with 8 tori on the F theory side, such that it's 6 torus in the base? Because in these models, it's expected that you have determinal singularities, right?
So you want a T6, you said?
I want a T8.
Yeah, people have studied T6, of course, which is in type 2b or type 2a or whatever. So yeah, people have studied T6. That's one of the old things people have studied. That part is not new. But nobody studied from the viewpoint of F theory because coupling constant is constant, so it's really type 2b. Thank you.